Hi, I'm Yue Yang. I'm going to present our work, Learning Convex Decomposition via Feature Field. So what is convex decomposition? Well, convex decomposition is the algorithm that approximates a detailed, non-convex shape with a set of simple convex components, so that the union of these convex components could approximate the original shape. Here, each colorful region corresponds to one convex polyhedron. It turns out that it is a powerful tool for problems such as collision detection, distance queries, and skeleton extraction, which is computationally intensive to solve for general meshes. However, if the input shape is a collection of convex polyhedron, many problems could be formulated as a convex optimization problem, and efficient algorithm can be specially designed. In fact, using convex components as collision proxy for actual scenes has become a standard practice for many game engines to model collision and interaction. And you might not realize it, you might be using this algorithm every day if you are working with a physical simulator, since all of them use convex decomposition for collision detection. Despite its fundamental and ubiquitous role, it is actually a very challenging problem, because finding the exact convex decomposition of the shapes has been proved to be NP hard, and many algorithms output a large number of the small convex components, making it impossible to use for real-life application. Instead, people relax the problem to approximate convex decomposition, where it only requires to approximate the shape so that it generates way less of the convex components, making it practical to use. Naturally, a good convex decomposition would maintain a high reconstruction qualities by minimizing the number of parts. Notice that it is actually two conflicting matrices, where you have to sacrifice one to get better in another one. However, it is still a very challenging problem with enormous decomposition search space. Classical method relies on many heuristic assumptions, such as limiting decomposition to exit a line cut or select the shape beforehand to make search space trackable, while learning-based method does not scale well to open-world data. And we also want to develop methods that support different 3D modalities, such as 3D model, 3D Gaussian sparse, or 3D scan, because in generative AI area, geometry does not always come in mesh form. And we also want the computation to be fast. So how can we build an algorithm that's for convex decomposition that achieve all of these goals? We think that the key idea is via feature learning. In particular, we want to use feature learning to build a feed-forward model for open-world convex decomposition. By feature learning, we mean that given an input shape, we train a coordinate network which learns to map every point on the shape to a feature vector so that we could form a feature field of this shape. And here we visualize the descent between features via principal component analysis. So the key idea of our method is to learn a set of features on the surface of the shape, such as the distance between 2 points of the feature space indicates whether these 2 points will lie in the same convex components. And then we can perform clustering using the off-the-shelf clustering tools like k-means clustering or agglomerated clustering on this feature and get a good partition of the shape. And the convex whole of this partition will use the final convex decomposition. Although it seems like a good plan, a key challenge is that we do not have data. In fact, we do not have large-scale peer data for shape with its convex decomposition. So we develop unsupervised geometry laws, which allow us to train without data. Our method is inspired by classical geometry definition of convexity. A shape is convex if for any 2 points, the line segment connecting them lies entirely inside the shape, and refer to this kind of points pair as convex pair. And non-convex pairs naturally means that point pairs whose line segment passes outside of the shape. And this notion of convex pairs allows us to formulate the convex decomposition algorithm as a discrete optimization problem. Intuitively, a good decomposition maximizes the number of convex pairs that belong to the same components, such as in scenario 1, where convex pairs shown as xy all belong to the same components, but not in scenario 2, where convex pairs are located at different components, so that we optimize for good partition that for all the convex pairs of the point on the shape, we want to make convex pair within the same components as much as possible. But this discrete optimization problem is often hard to solve, so we relax it to a continuous optimization problems by introducing a feature field. And instead of counting the convex pairs in the same component, we seek to minimize over the feature fields the feature descent of all the convex pairs on the same shape. But that is not enough, because merely minimizing the feature descent of the convex pair would result in a trivial solution where all the features on the shape would just equal to a constant. So we want to add another term that separates this feature descent of non-convex pair. In short, we have two terms. One tries to push the convex pair together, and one tries to push the non-convex pairs apart. And this is incredibly similar to the notion of contrastive learning, where you have convex pair as a positive example, which will pull features together, and non-convex pairs as negative example, which would push features apart. So we just use a triplet-based contrastive loss to supervise our network. To sample the triplet used for contrastive loss, for each of the source point, we cast ray towards inside hemisphere of the shape, and the endpoint it hits is regarded as a positive samples. And then we randomly sample points on the shape and cast rays towards the source point to test its visibility to get negative samples. Based on this objective, we train a feed-forward model that takes a point cloud as input and predict the feature field of that shape. The point cloud will go through several convolution layers and transformers to predict the feature field parameterized by the triplet. At train time, it is supervised by the contrastive loss on 300,000 shapes for the observers. Remember that no supervised data is needed, just a bag of shapes. And at inference time, the features are clustered to split the shape and converted to convex components. So now you have the features. How do you get a good decomposition algorithm that have granularity control? That's why we additionally propose a recursive decomposition algorithm, which basically recursively refines the convex decompositions by splitting one convex to smaller ones until the termination condition is met on each of the individual nodes. Here we accept targeted number of components or reconstruction quality as termination condition. Compared with all the previous learning-based and classical methods, our method generates geometry with more reasonable and accurate decomposition with fewer number of components required. For example, if you look at the feet of the elephant, only our method makes the feet separated. And in terms of quantitative evaluation, we evaluate the number of components, the chamfer distance reconstruction qualities, and we also additionally measure the degree of convexities, and our method outperforms previous methods in all of these metrics. By adjusting the clustering method, our method can generate decomposition at very granularity levels, all from the same feature field, and our method outperforms baseline level at all granularity levels. Since our model is conditioned on point cloud as input, we support different 3D modalities such as 3D CAD scan, 3D scan, and 3D Gaussians, as long as we can sample points on the geometry. Our method generates convex shape directly usable in physical simulators and achieve fast collision detection compared to original mesh form. Interestingly, our method achieves some degree of semantic decomposition even without relying on any semantic-related supervision. In the future, it will be interesting to see how we could integrate convex decomposition to more 2D or 3D semantic supervision signal, such as path label, to achieve semantically more meaningful convex decomposition. That's all for our work. Thank you for watching.